Good morning, everyone. There is a problem in Teams. It's not working, it seems. So let us continue on this Zoom link, but in about 45 minutes, it will end. I think so. If it doesn't end, then it's okay. But there's a possibility this will end at about 45 minutes. Then we will restart with another link. So let us continue from where we stopped last time. So the last Monday we didn't have the quiz because I didn't cover sufficient to have a quiz, and I missed 1 hour last Friday. So I'm going to update, catch up that 1 hour this Friday. So let me take the slides. We don't have quiz this week, but we will have quiz next Monday. So this Friday, I'll be taking tomorrow I'll be taking a class, not 1 hour, but I'll try to take at least one and a half hour or maybe 2 hours. So if you have any class after 9:30, then I'll continue that and record and post it. So let me share the screen. So we were looking at cables and arches. The first part is cables. So we have derived a few equations, and you can remember that we did this problem as well. So let me once again revise you the theory behind cables, and then we can continue with another problem. So cables are a type of structure, cable state structure. So when trying to find the forces acting in a cable, so if you look at a cable like this, then you may have this tension acting on it because the cables can carry only tension, and there can be a load acting on the cable. So if we consider the equilibrium of this, then we can derive this equation. So that is the equation we have derived. So if you consider the equilibrium of the cable, let me copy this as well. So if you consider this, then if you take horizontally, then this is the equation you have, that is T cos theta, this component, and plus, so T cos theta is in the negative direction. In the positive direction, T plus delta T cos theta plus delta theta, that is equal to 0 if you consider in the horizontal direction. So if you look at that, then as theta approaches 0, this if you divide this by delta x, all of them, I mean, because as theta approaches 0, delta x will approach 0. So this will become 0 and this will become 0 and this will become dt over dx cos theta. So that dt over dx cos theta is equal to 0. So that is the first equation. As delta x approaches 0, theta will approach 0. So that is the first equation. So this is applicable to any cable. Okay, so not just this cable, any cable. So, and also you can consider the vertical balancing all the vertical forces. So that is T sine theta acting downward, then W naught into X acting downward. So W naught into delta X acting downward. And T plus delta T sine theta plus delta theta is acting upward. So this component is acting upward. So if you take that equilibrium, then this is the equation, and then as delta x approaches 0, this becomes 0, and W becomes W naught. Okay, it's not. It will not become 0, but it will become W naught, and this becomes 0, and then the d theta over dx sine theta is equal to W naught. This is the second equation. So this is also valid for any application, any cable. So the two equations we have dt. So equations. Cables. So equation 1, dt cos theta over dx is equal to 0. Okay, so dt cos theta dx is equal to 0. Other one is dt sine theta over dx is equal to W naught. Okay, so other one, equation 2. dt sine theta over dx. So this is valid for any cable. So basically we will start with this equation. Then we need a relationship. You might remember we have derived a relationship that is this one. Okay, so this is W naught delta x into delta x by 2. That is taking moment from so taking moment at this point at O. Okay, so taking moment at O. So when you do that, you have this equation, that is W naught delta x is the load and it is acting at delta x by 2, that is counterclockwise. So T cos theta into delta y is clockwise, T cos theta into delta y is clockwise, and T sine theta into delta x 0. So now again this one, as delta x approaches 0, okay, so if you divide this by delta x, then it as delta x approaches 0, this becomes 0. So now here this is t cos delta x over delta. So that this dy by dx into t cos theta. Here this is t sine theta. So dy by dx t cos theta is equal to t sine theta, and we get another equation dy by dx is equal to tan theta. Okay, so the equation 3. Dy by dx is equal to tan theta. Okay, so these are the three equations. So here the theta is the angle that, or when you have the parabolic or the increase of the angle in the cable. W naught is the load acting on the cable, and the x and y are distance. Y is vertical distance, x is horizontal distance. So now let's take the second problem. So here there's a cable AB is subjected to a uniform loading of 200 Newton per meter. So there's a 200 Newton per meter is acting on the cable. If the weight of the cable is neglected and the slope angles at A and B are 30 and 60 degrees. So it is not 0 here now. It is 30 here, 60 here, respectively. Determine the curve that defines the cable shape. So we need to define the cable, the curve that defines the cable shape. So that equation will come from this y and x. So if you integrate this one, you will get something like, if you substitute this into a format, and if you integrate, you'll get something in terms of y and x. Okay, so that is the relationship we would like to derive now. Okay, and the maximum tension developed in the cable. So let me copy this one. So work example 2. Okay, so example 2. So determine the curve that defines the cable shape. Curve that defines the cable shape and maximum tension developed in the cable, and maximum tension in the cable. So in this case, we know that these are the equations we have. So we need to use these equations. Okay. So now here, the load acting on this is 200 kilonewton meter. So this is 200 is acting on this one, 200 Newton meter. So the dt sine theta over dx is W naught 200. Okay. So if you use equation 2, dt sine theta over dx is 200. So if I integrate this one, t sine theta is 200 x plus c1. Okay, because I'm not integrating in a range. Okay, t sine theta is 200 x plus c1. So you can remember that in the previous examples also we did the same way. We integrated. Okay, we integrated t sine theta and t cos theta. So like that we have to work out. So t sine theta is 200 x plus c1. Then the second equation is this is second. First equation, if you use dt cos theta over dx, t cos theta dx is 0. That means t cos theta is equal to c. 2. So that's a constant. That means if you take a horizontal component of the tension acting in this cable, and that horizontal component is constant anywhere. So what we can do now is we can, if you look at this tension here, so there will be a tension at this point. See, at the point A, there will be TA, and there will be a point where TB. Okay, so we know the angle at these points A and B. So we can use this one to find the tension value. So T cos theta is constant. That means TA cos 30 should be equal to TB cos 60, because horizontal component in the cable anywhere is constant. So if we consider horizontal tension component, so TA cos 30 is C2 and TB cos 60 is C2. Okay, that is correct. So now we can have a relationship between the TA and TB. So that is TA cos 30 is √3/2 and TB cos 60 is half. So we have a relationship that is TB is equal to √3 TA. Okay, that is one relationship. Then if we use this second equation at A, okay, at A, the tension is TA sine 30 is equal to 200x. X is 0 at point A. So that is 0 plus C1. Now, if you look at point B, that is TB sine 60 is equal to 200 into 15x plus C1. Okay, 200 into 15 plus C1. So now if I subtract, say this, if I mark this one as equation 1, 2, 3, if I subtract 2 from 3, TB sine 60 is √3/2 minus TA sine 30 is half is equal to C1 will cancel off 200 into 15, that is 3000 Newton. So now we can substitute TA or TB in terms of TA. So we know that TB is equal to √3 TA. So if I substitute here √3 TA into √3/2 minus TA over 2 is 3000. So if I take this one, it'll be 3 TA minus TA is 6000. I bring the 2 on this side. So 2 TA is 6000 Newton. So TA is 3000 Newton. So if TA is 3000 Newton, TB is √3 TA, that is 3000 root 3 Newton. So now we have the two values for TA and TB. So TA is less than TB. So that if you look at the tension here, it's the tension is increases with the angle. So the T cos T30 is TA cos 30 is C2. So we can find C2, we can find C1 as well. Okay, we need that. So now we need to find the C1. Before that, let us go to this equation. That is dy by dx is equal to tan theta. So dy by dx tan theta, that is equation 3. So if you take these two equations, t sine theta is equal to 200, so plus C1, t cos theta is equal to C2. So if I divide t sine theta over t cos theta, I'll get tan theta. So t sine theta is 200x plus C1. T cos theta is C2. Okay. So now I need to find C2. So C2 is TA cos 30. So TA is 3000. Cos 30 is root 3 by 2. So that is 1500 root 3. I'm sorry for the interruption. There's a drop in the signal. So now I have stopped here, right? Can someone tell me whether you disconnected before this one or at this point?
At that point.
Pardon? Hello? Can you spell a little bit louder at this point?
Yes, sir.
Okay, thank you. So C2, if you substitute in this TA cos 30, 3000 root 3 by 2, so 1500 root 3 is C2. And similarly, I can find C1 as well. So TA sine 30 is equal to C1. Okay, so TA sine 30 is C1. So TA is 3000. Sine 30 is half is C1. So C1 is 1500. So if I substitute that in this equation, to the 200x plus C1 is 1500. This is 1500 root 3. So that is 2 over 15 root 3. If I cancel 100, 2 over 15 root 3x plus 1 over root 3. So that is the equation dy by dx. Okay. So now if I integrate this once, I'll get y is equal to 2x squared over 15 root 3 over 2 plus 1 over root 3x plus C3. Now, the C3 will be determined from our boundary condition when x is equal to 0. When x is equal to 0, y is equal to 0. So when x is equal to 0, y is equal to 0. Therefore, C3 is 0. So the equation that governing the shape of the curve is x squared 15 root 3 plus x over root 3. So this is the shape of the curve. Okay, or shape of the curve of the cable. Curve of the cable. And the maximum tension in the cable. So you can see that TA is 3000. TA is 3000 and the TB is 3000 root 3. So the cable, if you look at the component, there is a T cos theta which doesn't change and T sin theta which changes with the length x. So the maximum T sin theta value will be there when x is max. Okay, so there are two equations. T cos theta is C1 is 1500, C2 is 1500 root 3. Then the T cos, so T sin theta is 200 x plus 1500 root 3. So with x value, T cos theta doesn't change. T sin theta increases. Therefore, the maximum T sin theta will be at x max. X max is 15 meter. So where the maximum tension, so because the tension in the cable is a sum of these two, T cos T squared cos theta, and okay, now it's going to end in 10 minutes. Then I will send another link for another meeting that you can join. Okay. That's why I prefer Teams, but Teams today it didn't work at all. So let me reschedule another. It's 9:40. So that's the link. But when this stops, you can join from that link. So the T value, so T squared cos squared theta plus T squared sin squared theta is going to get us the the T value. So there's a horizontal component and vertical component. So vertical component increases with the length, horizontal component doesn't change. So the maximum tension will occur at B. So therefore T max is equal to TB. So that is already we have found TB. That is 3000 root 3 Newton. So 3000 root 3 Newton. So this is the maximum tension in the cable. Okay, this is the maximum tension in the cable. And this is the shape of the cable. Shape of the curve of the cable. And this is the maximum tension on the cable. Okay. So this is how we can approach this cable problem. Now let me take this one. So here it's a bit different. Now if you look at this, the beam AB and BC are supported by cable that has a parabolic shape. So this cable has a parabolic shape, and AB and BC are supported by this cable. Determine the tension in the cable at points D, F, E, and the force in each of the equally spaced hangers. So the force in each of these hangers. So that is what the question asks. So now what we need to find is this curve is parabolic. That's fine. And you need to find the tension force in each of the equally spaced hangers. So these are the hangers. So equally spaced hangers. So you need to find the force in this one. So this 8 kilonewton is carried by this cable, and this equally spaced cable, it should carry equal load. Otherwise what will happen is there will be a force should be F on each of these. Otherwise what will happen is this shape cannot be maintained. Okay. So, and another point is there. Now here you have to take this okay, now for example you have to mark this one as F, 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 and there is a 2 supports as well. Okay, so there is a partially the load will be carried by the supports, partially by the cable. Okay, so now we can use this one to work out our problem, and we'll see how to do this. So now this is going to end in 5 minutes. So let me stop this one. I'll start the next one. Okay, so you please join the next one. In the mean, can you copy that invitation link into some place so that you can, if I'm not sure that if I end this session, you may not be able to see this message. So that's why I'm asking you to copy this. But in the future, we will use Teams. I think Teams server might be having some problem. I think that's the issue today. Okay, so I will join you in the next link. Now I'll stop this one, and so it will start saving the recordings. Okay.